Hello everyone, welcome to my YouTube channel. So today I am going to discuss TIFRGS 2025 questions. Okay, so in this video I am going to discuss all the true false problems, and in another video I will discuss all the MCQ problems. Okay, so let's start. So the first question, so this is the question paper, and for the first question it is saying that there exists a linear polynomial Px inside Rx for which there exist exactly two subsets S in R such that Ps equal to S such that cardinality of S equal to 2, right? So it says that P of X is in the polynomial ring Rx. Okay, and you can find two subsets S1 S2 inside real number exactly 2 such that P of Si equal to Si I equal to 1 and 2 and order of Si equal to 2. So let's say assume that S1 equal to S1 comma T1 and S2 equal to small s2 comma T2. Okay, now P is a linear polynomial, right? So if it is a linear polynomial, then Px can be written as Ax plus B, right, where A and B are real number. Now it is given that P of S1 equal to S1. So let's say P of S1, so this is inside S1, so let's take S1, and P of T1 equal to say T1. Then what will happen? Then it is same as AS1 plus B equal to S1 and AT1 plus B equal to T1. Then A times S1 minus T1 equal to S1 minus T1. Simple computation. So this problem is very simple problem, just a simple small computation. Okay. Now since S1 and S1 not equal to T1 because they are distinct element, so A must be equal to 1. Now if A is equal to 1, then what is Px? Px equal to X plus B, right? So then P of S1 equal to S1 plus B, S1 plus B, and that is equal to S1, so this will imply B equal to 0. So then Px must be equal to X. But in that case you can find many subsets of order 2 that satisfies that P of S equal to S. In particular, you can take any 2-point subset that will automatically. But in the question it is saying that there exist two subsets that satisfies this property. So that is not the case, right? So this is a contradiction. So now what can happen if P of S1 equal to T1 and P of T1 equal to S2, AS1, right? This is the case 2. Okay, so this is case 1. Again, then what will happen? AS1 plus B equal to T1 and AT1 plus B, this is equal to S1. So then from here A equal to minus 1, right? Again, because A of S1 minus T1 equal to T1 minus S1. So from here A equal to minus 1. So then Px equal to minus X times plus B. So minus S1 plus B equal to T1. So B equal to T1 plus S1. Okay, so B equal to T1 plus S1. So Px equal to minus X plus T1 plus S1. Now what about other subset? S2, right? So then P of S2 equal to what? P of S2 equal to minus S2 plus T1 plus S1. And P of T2 equal to minus T2 plus T1 plus S1. Okay, so then in this case also what will happen? Basically I need to show that only two subset satisfies this condition. That is not possible. Okay, there could be many extra subsets that satisfies this condition from here. So if this is true, P of S2 equal to minus S2 plus T1 plus S1, so this case 3, or you can say the sub case P of S2 equal to S2 and P of T2 equal to T2. For that, then what will happen? Right? Then what will happen? If P of S2 equal to S2, then 2S2 equal to T1 plus S1. Right? So then S2 equal to T1 plus S1 by 2. Okay, and 2T2 equal to T1 plus S1, then T2 equal to T1 plus S1 by 2. But that is a contradiction because T1 and T2 and S2 are distinct. That's what we assume. So then P of S2 must be T2, case 4, and P of T2 must be S2. Right? So then S1, this is T2 plus T1 plus S1, this is basically S2, right? So then T1 plus S1 equal to T2 plus S2, right? That's the condition that should satisfy. But then you can take S1 T1, S2 T2. You have infinitely many choices that satisfies that S1 plus T1 equal to S2 plus T2, right? And if you put that value, then for that polynomial particularly, for that linear polynomial particularly, you have many choices. So only two subsets S that satisfies this condition. This is not possible. Okay, so observe in this question it is saying that what is the question? Yeah, so observe in this question that they are exactly, so this is important, they are exactly two subsets. That is not possible. If there are subsets, then there can be infinitely many subsets. Okay, so the exactly two is not possible, so that's why this is false. Okay, so this problem is very simple problem. You just put the value and just check, because this is a linear polynomial, right? So that's why it's not very difficult to solve. Okay, so now it is question number 2. This is very simple problem, and if you know fundamental theorem of finitely generated abelian group, then you can do it easily, right? This is directly from, or you can say structure theorem for finitely generated abelian group, but it is a finite group, so you have it for finite abelian group, right? So this is basically, so 2025 is what? This is what? If you 5, then it is what? 405. Then you have 5 square times 3 to the power 4. So prime factorization is 3 to the power 4 times 5 square. Okay, so then you can easily compute. You know that how many abelian groups are there. You have to basically find out the partition of this number, right? So partition of 4 and partition of 2. Okay, so then there are exactly 10. So hence there are exactly 10 abelian groups of order 2025 up to isomorphism. This is directly from the finite abelian group structure theorem. Okay, so now this is the question for question number 3rd. If a subset of R is uncountable, then there exist uncountable many elements x in A such that x is a limit point of A minus x. Okay, so the question is saying that A is a subset of real number and it's an uncountable subset. Then there exist uncountable many elements such that x is a limit point of A minus x. Okay, so that means it is enough to show that A contains uncountable many limit points. A contains uncountable many limit points inside that, right? So A itself contains uncountable many limit points inside it. So you can if you can show that number of isolated points is at most countable, then you are done. So this is basically a theorem. I don't know whether this is done in some specified book or not, but it can be proved. Okay, so it can be proved. So how to prove it? So the statement that I want to prove here, so for this 3rd part, so show that number of isolated points is at most countable. Okay, for any subset of real number, for any subset A inside R. Okay, it is at most countable. So now okay, so this is the case. Okay, so now my point is that how to do it. Okay, so this is not very difficult to do. So what is definition of isolated point? So isolated point means there exists an interval, AB such that right, if x is an isolated point of A. This is the definition, right? So if little x is an isolated point, so that means there exists an open interval AB such that this intersection A is the singleton x, right? So now you can choose A and B to be rational number. So you can choose the interval to be rational endpoint. In particular, you can choose the small enough interval. So first take any AB, then you can choose some rational number inside that, and you can choose the small interval that will give you this, right? So then this intersects A is x, right, where A and B are rational. So then if you can define a map from Q to what? You can define phi of any point x equal to this ax comma bx. Okay, so I think it is better to write this AB interval as ax comma bx, because it depend on x, right? Depending on x, little x. So I should not write this interval. It's a pair. Okay, it's a ordered pair, ax comma bx ordered pair in Q2. Okay, and show that phi is injective. Okay? Phi is injective. Why injective? Because see, if two things, say A comma B, if phi of x equal to A comma B and phi of y is also equal to A comma B, that means what? A comma B intersection A is singleton x, and A comma B intersection A is singleton y by definition, right? And then it will automatically implies x equal to y. So this is an injective map. So it's an injective set map, and Q2 is countable because Q is countable, right? So since Q is countable, so then Q2 is also countable. So then isolated is countable. It can be finite, but it is countable, at most countable. So hence, since isolated points are at most countable, then all the other points must be limit point of A itself. So that's why this is true. There exist uncountable many elements of A, which is limit point of A. That's why this is true. Okay. Now by using the same kind of concept, you can show the fourth one. Fourth one is almost the similar kind of problem. So the fourth problem asks the question that there exists an open subset of R with uncountable many connected components. Similar thing will hold, right? There exists an open interval such that it contains uncountable many connected component. Okay, so first thing, observe, there exists open subset such that it contains uncountable many connected component. Okay, how to do it, right? Okay, so let A be open in R, right? Right. So now if you take any point x in A, since A is open, there exists an open interval containing x inside A. Now this open interval is always connected, right? Is connected. So that means it must be contained in some connected component. Is contained in some connected component of x, right? Okay, sorry, not x, it should be a connected component of a. Now if it is contained in some connected component, so that will automatically imply you can always find in every interval, you can always find a rational number. So choose a rational number, p inside this interval. Okay, so that is contained in some connected component. So what does it imply? So this will imply that every connected component, this will imply every connected component must contain a rational number. So every connected component must contain a rational number, and the connected components are disjoint, right? Any two connected component, if you take two distinct connected components, they must be disjoint. So that means there can be at most countable many connected components, because every connected component must have a rational number, okay, and they are disjoint. So the rational number inside every connected component must be distinct rational number. There is no common rational number, right? So that will automatically implies that, okay, so right, so that will automatically implies that number of connected components is at most countable. So here we are using the property that A is open. So that's why if you choose any point, there exists a open interval that containing that point, and that is inside A. And any open interval is connected, so it is inside that connected component, and inside every open interval you can always choose a rational number. That is important, that's argument is important. But if it is not open, you cannot say anything, right? Because in particular, if you take, say, collection of all irrational numbers, right, then every singleton is a connected component for that, right? And then the number of connected components must be uncountable. But since irrational numbers is not open, so that argument will not be true. But here the openness is quite important, so be careful, okay? So try to follow all the arguments. See, this is the questions of standard of questions of TIFR, that if you have concept, if you have basic concepts, if you know basic properties and all, then you will be able to solve most of the problem, okay? So most of the problem will not require some advanced machineries and advanced questions, okay, advanced concepts, okay, because these problems are also for BSc level students also, right? Those who are going to give integrated PhDs exam, these type of problems are for them also, because the question paper is same. So that's why they are not basically giving questions which requires much more advanced concept, okay? They are trying to give problems which can be solved by elementary ways. Elementary in the sense that only BSc level knowledge will be enough to solve more than 60 to 70% questions of the paper, okay? So that's why try to understand the concepts very well and try to approach in this way, okay? So, and those who have solved some previous year problems, they can get some idea. So solving previous year's problems is very, very important, okay? So that's why this problem is done, okay? So that's why this problem is done. So that's why it is false, because there can be at most countable many connected components, okay? So now this question number 5, that xd a non-empty complete metric space T from x to x be a continuous function such that T square is contraction. So then there exists then there is a unique element x such that Tx equal to x. First of all, this is related to Banach contraction principle, okay? So those who don't know this theorem, they are not able to solve this problem. But those who know this theorem, they should know the proof of this theorem, which is not very difficult, and they should know what is the statement. So by using Banach contraction principle, T square is a contraction. So T square has a unique fixed point, right? So T square has a unique fixed point because T square is contraction. So T square is a contraction, and T square has a unique fixed point. Okay. So since T square has a unique fixed point, so that means T square x equal to x. Okay. So now observe, if tx has if tx equal to x and ty equal to y, then t square x equal to x and t square y equal to y, which is a contradiction. So this will tell us that t has at most one fixed point, right? If there is two fixed points, then that fixed points of t must be fixed points of t square also. But since t square is contraction by Banach contraction principle, it has unique fixed point. So t has at most one fixed point. Now my claim is that x is the fixed point of t. Why? Because see, what is t of tx? What is this? This is x by definition, right? Right? So now if you have, so what is t cube x? T cube x is same as tx because t square x equal to x, right? So then t square of tx is same equal to tx. Then tx is also a fixed point of t square. So tx is fixed point of t square. But tx has a unique, t square has a unique fixed point, right? So that means tx must be equal to x. So x is the fixed point. So hence this statement is clear. Okay, this is true. In particular, this is true that if t to the m for some m is contraction, that will imply t has unique fixed point. By same argument, not just t square. If t to the power m is contraction for any m, then t has a unique fixed point. Okay, so that's why this problem is done. Okay, now problem number 6. Problem number 6 is S2 is this, d S2 to S2 is a Euclidean metric, and S2 to S2 is a function such that d of fx comma fy is distance of x comma y for all x y in S2, then f is surjective. Okay, so this is a general theorem. There is a general theorem. Those who know metric space and those who have done some problems related to compact metric space, they will know this. If you have read some book of metric space, there must be this problem. In particular, I can suggest one book, that is Metric Space by Kumarasen. That is the standard book most of the Indian people are following, and it's a very nice book. I have also suggested that book in my previous videos as well. So if you have read this book, or if you have read the chapters on compactness, then you will encounter this problem definitely. Okay, so this is actually a general statement, but here it is asked on some special condition. Okay, so what is the statement? First of all, observe that d of fx comma fy is same as distance of x comma y for all xy in x, where f x to x, where x is a metric space. This implies f is isometry. This is the definition. Isometry definition. Okay, so this is the definition of isometry. And what is happening? So there is a theorem. I don't want to prove it because see, this is a standard theorem which you will find in every book, so I don't want to waste time. Those who know this theorem, they should be able to answer. Those who don't know, they should look at the proof and then they should try. Okay, and even if you have no book, you can just search it in Google. This is a standard theorem, so you will find many proofs available in internet. So the theorem is that isometry on compact metric space is always surjective. Okay, so now look at this problem. The problem is saying is that isometry on S2. Now S2 is the what? S2 is the sphere, right? S2 is sphere inside R3. So it's a closed bounded subset. So in Rn, any closed bounded subset must be compact, right? Compact if and only closed bounded in Rn, right? So that's basically the Hein-Borel theorem. So then S2 is compact. So since S2 is compact, it must be surjective by that theorem. And in 2023 also there was I don't remember, not in 2023, but maybe some years ago, there was a problem that that was related to the same theorem. Okay, so that's why my suggestion is that try to solve previous year question papers as well. Okay, so that you can get some idea. So these are the standard theorem that is always used to solve this kind of problem. Okay, okay, so that's why this is true. Now I'm coming back to the problem number 7. So what is it saying? It's saying that see the continuous functions on closed interval 0 1, set of all continuous function, and we can define a metric on this. They're basically sup metric. So with respect to sup metric, if we take the subset that integral 0 to 1 fx ft dt that is not equal to 0, that is okay. So yes, so then what I need to show? So this is this induced metric x is connected or not. Okay, so x is connected or not, right? It's a very simple thing. So what I can do say, so say C01 to R f, or I should say write phi of f equal to integral 0 to 1 ft dt. Show that phi is continuous. Very simple. Those who have read metric space, they already encountered this continuous function. This is the continuous function, right? Okay, so this is a continuous function. And now what is phi of x? Phi of x is minus infinity to 0 union 0 comma infinity, right? So now image of connected set, so under continuous map, image of connected set is connected, right? Continuous image of a connected set is connected. So if x is connected, then image must be connected, but image is disconnected because minus infinity to 0 union 0 to infinity, that is not connected in R. So that's why it is disconnected. It's a very simple problem. So it's a doable problem and it's an easy problem. Okay. Now question number 8. Those who know orthogonal matrix, what is its property, they should be able to solve it. It's a very simple problem. So it says that SO4, that is spatial orthogonal matrix, that means the orthogonal matrix of order 4 with determinant 1, right? You know the orthogonal matrix has determinant either 1 or minus 1, because you know that A determinant of A is same as determinant of A transpose, and A transpose equal to identity, so determinant of A square equal to 1, so determinant of A is 1 or minus 1, right? So that means determinant of A is positive, that means its determinant is equal to 1. So a special orthogonal. So now then every eigenvalue must be 1 or minus 1. This is weird, right? This is not, this shouldn't be true, because in orthogonal maybe the matrix is orthogonal, but the eigenvalue may not be real, right? Eigenvalue may not be real. If the eigenvalue is real, then it is 1 or minus 1, definitely, right? If the eigenvalue is real, then it is 1 or minus 1, but otherwise it is not true. Because one thing one know, if you know some concepts of inner product space, then you know that orthogonal matrix, all the eigenvalues has unit norm. The norm is unique. Norm is 1. Norm is 1. But if it is, so that's why if it is real, then it is 1 or minus 1, but it may not be real. So it can be complex number as well, right? In particular, you can take some 2 by 2 matrix, right? So on the 2 by 2 case, you know what is the standard thing, standard rotation matrix. You can take rotation matrix. In case of rotation matrix, this is always orthogonal. That's the typical example in R2 or on R2. So on in case of M to R, you can take the rotation matrix, right? Which is basically cos theta, sin theta, minus sin theta, cos theta, that matrix, right? So in this case, for this type of matrix, for any theta, this is orthogonal, right? For any theta, this is orthogonal. But you can take this matrix, and a simple example, what should be a simple example? And in this case, it is asking about 4, order 4, right? So it is asking about order 4. But if you can get some order 2 thing, then you can, okay, one second. I want to add some page. Okay, so I don't know what's happening. 1 second. Okay, so maybe I should write it here, that so my matrix you can define this way, right? Cos theta, sin theta, minus sin theta, cos theta, 0 0 0 0 0 0 0 0 1 0 1 0 1, something like that. So this is a 4x4 matrix, and choose some theta such that for this matrix has eigenvalue complex number which is not real. So that will automatically give you an eigenvalue of A also. This is orthogonal matrix, but then determinant is positive, but you know all the eigenvalues are not minus 1 1, so that's why this is false. Okay, now question number 9. T is the endomorphism or finite dimensional real vector space. W is image of T. Then T prime is the restriction operator on T. Then T and T prime have same trace. This is just a definition. Just a definition. So how to solve it? Okay. So W equal to image of T. And then we have to define T restricted to W, from W to W. Why? Because image of T is T invariant. So image of T is T invariant. So since image of T is T invariant, you can define the restriction operator. Now it is asking that the trace of this operator and trace of T must be same. So it's the same, very basic thing. So what you should do? First, choose a basis of image of T. So beta be a basis of image of T. Right? So say beta, so it's a finite dimensional case, right? So beta equal to say V1, V2, or I should write W1, W2 up to Wk, and say gamma equal to W1, W2 up to Wk, Vk plus 1 up to Vn. This is the basis of X, a basis of V. Then we can find the matrix representation. So what is T of W1? T of W1 is same as T restricted to W of W1. Right? This is by definition. Then you get T of Wk, which is same as T restricted to Wk. This is by definition restriction operator. Now what is T of Vk plus 1? Okay. So what is T of Vk plus 1? So T of Vk plus 1 is in image, is in the image of T. So since this beta is a basis, that means T of Vk plus 1 must be C1 W1 plus C2 W2 up to Ck Wk plus 0 times Vk plus 1 plus 0 times Vk plus 2, so on. Similarly, T of Vk plus 2, this is inside image, so this can be written as say this can be written as some linear combination of Wk plus 0 times Vk plus 1 plus 0 times Vk plus 2 plus 0 times all these things, because these parts are not in the image. So when you write the, so this thing is already in image, so this can be written as the basis elements of the image, and W1 to Wk, this forms a basis of image. So any vector in the image can be uniquely expressed as the basis element. So that for the extra vector, coefficient must be 0, right? This is the idea. So for extra vector, coefficient must be 0. So then if you write down the matrix representation, what will you get? You get, for the first block, you get the matrix representation of T restricted to W, and then after that whatever is there you can get, but in this lower part this is actually 0 matrix. This is actually 0 matrix, right? So that's why if you take the trace must be same. Trace of T. This is a 0 matrix, because so T of V, for T of Vk plus 1, upper part there can be anything, but lower part this is 0. Starting from Vk plus 1, all the coefficients are 0, right? And you write the matrix representation, you write this, take these coefficients and you put it as a column vector. So if you put it as a column vector, then this entry must be the coefficient of Vk plus 1, and this entry must be coefficient of vk plus 2 and so on, but all these terms are 0. Similarly here also these entries are coefficient of vk plus 1, vk plus 2 and all this is 0. So all these diagonal entries must be 0 starting from here. So ultimately trace must be same. This is the idea. Okay, fine. So now, so this is problem number 9. So now what is problem number 10? Every subgroup of S1 is a group under multiplication is a finite. It's completely false. Why? So you can just take e to the power 2 pi I times r, where r is irrational number. Okay, just take this g and take the cyclic subgroup generated by g. This must be inside S1 because S1 is as norm 1 vectors. So then this must be in S1. But if you take g power n, this cannot be identity. Cannot be identity. You cannot get 1 because r is inside irrational number. So that's why every subgroup under multiplication is not finite. But if you take r to be rational number, then after some multiple, high enough multiple, you can write it, you get it some integer, and e to the power 2 pi I n, where n is integer, that is always 1. But for irrational number you will not get it. For any multiple it will not be an integer. So that's why it will be an infinite subgroup. Okay, so that's why question number 10, this is false, that every subgroup of S1 is finite. That is wrong. Okay. Now question number 11, f from f to f homomorphism of field, then f is surjective. Okay, so this problem I will consider this problem as a moderate problem, because this requires some concepts of field theory. Those who know the field theory, mainly the PhD aspirants who has some idea about field theory, they should be able to do it. This is also not very difficult, or if you have some idea, then you can solve this. That see, if you have any field homomorphism, then it is always injective. Why this is so? Because kernel, when you have a field homomorphism, it is you need to check that kernel is trivial or not. But kernel is always forms an ideal, right? So if it is, so since it is a field, so only non-trivial ideal except f itself, it is the trivial ideal, zero ideal, right? So that's why kernel is trivial. So kernel is trivial. Now if f is surjective and f is always injective, that means, right? So if you have a field homomorphism of fields, then f is always injective. But now if f is surjective always, then f is automorphism, right? So that means any injective field homomorphism must be an automorphism, which is kind of not true, right? Not true in general. What you can do, you can take something, so you can take some field of imperfect field of characteristic P, okay? Imperfect field of characteristic P, if you take that, then if you take the Frobenius map, x goes to x to the power P, that cannot be surjective because by definition it's imperfect. So x to the power P, so there must be at least one field element which has no pth root. So this map cannot be surjective, x to the P, right? So that's why this is false. So I'm considering this problem as a moderate problem because this is not very trivial. You have to understand the basic concepts of field theory very well. So basically take characteristic P field, characteristic P imperfect field, and consider x goes to x to the power P, the Frobenius morphism. Okay, so then it is not surjective. Okay, so now I'm considering question number 12. See, question number 2, see, I always suggest you that linear algebra is much more easier portion to solve. If you have some basic concepts, if you think it properly, then there will be many problems which seems to be difficult, but it is not actually difficult. Okay, like this question number 12. You maybe you can think that okay, this might be a very difficult thing, but it's not a difficult thing. Why? So it is saying that given any linear transformation R2 to R2, there exists a linear transformation T1 and T2 such that 1, 0 belongs to the kernel of T1 and 0, 1 belongs to image of T2 such that T equal to T1 plus T2. So we want to write T as a T1 plus T2 such that T1 satisfies this property and T2 satisfies this property, right? So what can we do? what can we do? This is doable. Okay, so we want t1 of 1 comma 0 must be 0 comma 0. There is no other option, right? This is by definition. Then what should be t1 of 0 1? Okay, what should be t1 of 0 1? Let's define something, say 0 1. Let's try to define. Okay, then what should be t2? So then t2 of 1 0 I can define as t of 1 0. Why? Because I want t equal to t1 plus t2. So since t1 of 1 comma 0 is already 0, so if I define t2 of 1 comma 0 equal to t of 1 comma 0, then it is fine. And then what about t2 of 0 1? What about this? Okay. So I think I should not define this t1 first, because I want to define t1 of 0 1 based on t2. So let's take t2 of 0 1 equal to 0 comma 1. Okay, and then define t1 of 0 1 as t of 0 1 minus 0 comma 1. I can define it, no problem, right? The extraordinary the facility of linear algebra is that if you want to define some linear map, it is enough to define on the basis vectors. And since bases are linearly independent, it doesn't depend on the choice. There is no problem. You can define wherever you want to map it, right? You can define t of that basis vector to be anything, whatever you want. Okay, whatever property you need to satisfy, you can do this. This is the extra facility for linear algebra. So now if you define this, then t1 obviously a linear operator because I have defined already, and t2 is already a linear operator. Then what is t1 plus t2? T1 plus t2 of 1 0, this is must be t of 1 0, and t1 plus t2 of 0 1, this must be t of 0 1. So then t1 plus t2, since they agree on the basis vector, they must be equal. Okay, so that's why you can always write t as sum of t1 plus t2. Okay, but I want to consider this problem as a moderate to hard problem, in the sense that you may not be able to think it directly because it seems to be non-trivial to some of you, but it's not hard to do it. Okay, fine. So now, so this is the question number 12. We are done. Now question number 13. Question number 13, I should say that this is a doable problem. So that for any positive integer d, the set 10 to the power a minus 10 to the power b must contains d. Okay. So suppose if d so if d has a prime factor 2 or 5, then it is trivial, right? If d has a prime factor 2 or 5, okay, so if d has a prime factor 2 or 5, then it is trivial. Why? Then you can always find something. So let's take d equal to say 8, right? So you can take say d to be 40, and so say d equal to 5, so you can take the multiple of d to be what? You can take 40, 400, whatever it be, and you can write 10 to the power a minus 10 to the power b according to that. You can divide that, right? This will not be very difficult, right? So am I correct? I think it is correct, right? There is no problem. If d has a prime factor 2 or 5, then it is easy to do. Okay, so it says that it is distinct positive integers. So yes. In fact this is true, right? Because if d has a factor 2 or 5, then one can do it directly. There's no problem. Yeah, then it is fine. Yeah, but if d has an I'll request you to write down explicit proof. This is not very difficult. I want to give you as exercise. Okay, t has a prime factor 2 or 5, then it is fine. But if t has no prime factor 2 and 5, then what? Then GCD of 10 comma d equal to 1, right? So then 10 to the power phi d is congruent to 1 mod d, right? And 10 to the power 2 phi d, that is also congruent to 1 mod d. So then you can choose a to be 2 times phi of d, b to be phi of d. Then 10 to the power a minus 10 to the power b congruent to 0 mod d, that means d divides this. That means d divides this. So this is multiple of d. So that's why this is true. This is also a doable problem. Now question number 14. Question number 14 says that there exists a theta such that theta belongs to 0 comma pi by 2 and such that this will be sin theta plus sec theta plus cot theta. Okay. So I want to say one thing, that since it's a TIFR problem, don't think it directly. Whenever it will ask some question, try to use use your maturity and try to think it in a smart way. Okay. See, I can say you that in most of the problems in TIFR, when there is some equality problem or inequality problem, you can use some standard inequality. That is also one of them. Like Cauchy-Schwarz inequality is a very nice options, and in many years many questions comes that uses that. And also one simple inequality that we are going to use always, that is AMGM inequality. So this problem is going to be solved by directly AMGM inequality. So why? How to do it? So there is a theta. So first of all, observe that sin theta, sec theta, cot theta, all of these things are positive if theta belongs to 0 comma pi by 2, right? All these things are positive. Then you can use the AMGN inequality, right? So AM is greater or equal to GM. So then sin theta plus sec theta plus cot theta by 3, this is greater or equal to root over what? Sin theta times sec theta plus cot theta, right? So this is 1, sorry, cube root, right? Cube root of this. So this is 1. So then this is greater or equal to sin theta plus sec theta plus cot theta by 3. This is greater or equal to 3. This is greater or equal to 3. And when this is equal to 3, that will imply sin theta equal to cos theta equal to cot theta, right? That is not possible for theta inside 0 to pi by 2. Okay, right? 0 to pi by 2. See, if right, so if your theta is pi by 2, then sin pi by 2 is 1, right? Sin pi by 2 is 1. No, I should say that if theta is, yeah, so for theta, so for no for if you take any theta from 0 to pi by 2, they will not be equal. Yeah, that's the thing. So that's why there doesn't exist any theta. Okay. So hence this AMGM inequality, by using AMGM inequality you get this false. Now the question, problem number 15. This kind of problem always comes in TIFR. If you saw the previous year question papers, right? So for this you have to understand the symmetric group very well. This is a very well known group, and there are lots of properties available. You should read some book and you should get idea about the properties of the symmetric group. Then you can be able to solve it. Okay. So the question says that so AM is a positive integer and SM is a symmetric group on order M. A and B a positive integer such that every group of order M, there is the injective group homomorphism from G to SM. Then M greater or equal to N. Every group of order N. Whenever I want to give you one tips, that whenever some statement is given to be true for every group of particular order, then always try to think for cyclic group. Why? Because for cyclic group, you know that there exists exactly one group, right? One group up to isomorphism. So for cyclic group, if you fix some order that has, in that order every subgroup is cyclic, then you can easily, then it will be easier to verify or easier to check. So that's why my tips will be for this kind of problem, when some property or some question is asked about to solve every group of particular order, my suggestion will be that try to think about cyclic group. Okay, so that means what? Some order which has only one subgroup. That means any subgroup of that order is must be the cyclic group. Okay, so if you take that, if you see that, then what? So this shouldn't be true example, because see, even if m is small, sm group, the group sm must be bigger, right? Because the order of the group is m factorial, which is a huge number, right? For say for s5, m equal to 5, but order is 120, which is huge, right? Like, so that's why it is not necessarily true. In particular, if you take s8, m equal to 8 and 8, then it is 8 factorial, which is a huge quantity, right? But if you take, you know that any group of order 15 is cyclic, right? And 15 is a not very large number, but it's a large number which has every group order cyclic. So, and if you in s8, if you take a 3 cycle and product to it a 5 cycle, okay, they are disjoint, then this cycle has order 15, right? Because LCM of 3 and 5 must be 15. So this has order 15, so it will generate a cyclic subgroup of order 15. So then this example is wrong. M equal to 8, n equal to 15. Any group of order 15 which is cyclic must be isomorphic to this. So there is always an injective group homomorphism from G to that. In particular, you can take the generator of this G and you map it to this cycle, and this will automatically give you the homomorphism. G to the power m must be the cycle to the power that m. Okay, so that will give you the homomorphism. So then there is the injective group homomorphism G to Sm. This is true, but m is small. The only thing that you need to think about it, that in this way, that m, even if m is small, the order of Sm is very big. Right? Order of Sm is very big, so it is not very clear that why it should be true. Okay, so in TIFR problems, you have to first understand whether this statement can be true or not. First, you have to some logical guess, then try to prove it. Yes, some problems it may happen that you have some intuition, but that intuition may be wrong. So don't just give some tukka, or don't just give by using just some basic intuition. You shouldn't prove it. You shouldn't put the answer. You have to think it properly, but think logically, think in a smart way, so that you can get this idea. Like the way I'm thinking in this way, like SM has bigger order, like it's a very big order, 8 factorial. If you have, even if M is 8, it's 8 factorial, so it's a huge quantity. So that's why it is not even true. Okay, so that's why the question number 15 is actually a false statement. Okay, so now there are 5 problems left. First of all, the question number 16. Okay, so what is the question number 16? Okay, so before going to solve question number 16, maybe first try to solve some other problems first, because other problems are much more easier. So what about question number 17? 17 says that there are only finitely many subsets. I will put it as a moderate question, moderate to hard question, because you have to think it properly. This is not very difficult, but it's actually conceptual, or you can say that it's a if you are smart enough, if you think it properly, then you will be able to solve it. There is not much more concepts behind this. This question number 70 is a very simple problem, but you need to think it properly. So there are only finitely many subsets of subsets I inside the natural number, such that if you consider the subring, such that this will be subring, that for that particular indices of I, AI is a rational number. Other coefficients can be any real number, but for particularly that coefficient must be rational number. So if AI is rational, BI is rational, then if you add it, AI plus BI, that must be rational. For some it is always fine, there is no problem. The problem is about the multiplication. If you want to check subring, then you have to check not just addition, right? You have to check multiplication as well. So in problem number 17, you have to check multiplication, but for multiplication you have to check if ith indices, some I, P is P has some coefficient AI, Q has some coefficient BI, whatever it be, but some x to the power I has rational coefficient, x to the power I has rational coefficient in Q, then what about P dot Q? Does it imply x to the power I has rational coefficient? Okay, so for that, what you need to do, you need to just observe that what will be the coefficient of the product, right? So suppose p equal to a0 a1 x up to ak x to the k, and q equal to b0 plus b1 x plus bp x to the p. Okay, what about pq? Something. Now what is coefficient of x to the power I in pq? X to the power I in pq. So observe, it must be add of the coefficient, what? So constant term and x to the power I term of constant term of p and x to the power I term of q. Product of that two term give you a factor. Coefficients of a x term and x to the power I minus 1 term, that will give you 1. So a0, so this is basically a0 plus bi x to the I plus a1 plus bi minus 1 x to the power I plus a2 bi minus 2 x to the power I plus ai b0 x to the power I, right? This is the term, right? a2 b I minus 2 plus ai b0, right? Right. So now if I consider I to be, if I consider a0 or a1 starting from whatever, if I consider 1 to up to n, okay, so in to be 1 to up to n, okay, all the lower coefficients, okay. So for that, all ai's must be rational number for I less equal to n. Then if you do the product, for product, if you product, this x to the power I has coefficient rational number, because the coefficients of x to the power I must be contributed from the lower degree terms. If all the lower degree terms are rational number, then their product plus sum, that is also rational number. So that's why this subset is not finite. You can construct infinitely many subsets. In particular, if you choose I to be 1 to n for any n, that will give you that this is actually a subring. Okay, so that's why this is false. There are only finitely many subsets, that is false. Okay, now question number 18, that there are uncountable many continuous functions from q to 0 1. Okay, uncountable many continuous functions from q to 0 1. Okay, so this is also true. So how to do it? This is also a standard trick available in many metric space book or anything else. So standard trick, if you know this, then you can be able to do it. So continuous function is q to 0 1, right? So define fx equal to 0 if x less than r, fx equal to 1 if x greater equal to r. Okay, sorry, x greater than r. Okay, I should write, no, I should not write x, I should write right, x less than r, x greater than r for all x in q, because it is defined over q, where r belongs to irrational number. So for every irrational number, define this. So for idea, for every irrational number r in QC, define a continuous map, say fr from q to 0 1, fr of x is 0 if x is less than r, and this is 1 if x is greater than r. This is continuous because 0 comma 1, this is a finite set, so this is discrete metric space. So singleton 0 and singleton 1 are open, so inverse image of this open must be open. So this is also open because minus infinity to r intersection q, that is open, and it is r comma infinity intersection q, that is also open inside q. So hence this is a continuous function, right? So there are uncountable many continuous functions because there are uncountable many irrational numbers. So for every irrational number we can define a continuous function, and all these continuous functions are distinct. So that's why there are uncountable many continuous functions from q to 0 1. So now question number 19, f from r to r be a continuously differentiable function. Suppose there is a constant c such that f is injective on this, then there must be a constant d such that f prime is injective on this, right? Just think it graphically, right? So graphically you can think that, okay, so from some c f is injective, right? So f is injective, something like that, okay? So then f prime must be injective from some, but that is not true, right? Why that is not true? Because f prime can be anything, there is no property, right? In particular you can take the identity function. See, it's a horrible statement. I mean, very horrible statement, right? This is a very high claim. We shouldn't be true. You can take that identity function, right? This is injective on whole R. But what is the differentiation? This is just a constant function, right? F prime is constant. So there is no point of being injective. So question number 19 is very easy problem and very simple problem. You can just take identity function to be counterexample. Okay. Now what about question number 20? Question number 20 is a standard problem. If you have standard concepts, you will be able to solve. But it's a very nice problem. I like this problem. But this requires just a basic concept of continuity. Okay. So question number 20, what is this saying? So this says that f and g are closed interval 0 to r are continuous functions such that f dot g is 0, then one of f and g must be 0 on some open subset. Okay. So this says that f and g from 0 1 to r continuous such that f dot g must be 0, then f and or g must be 0 on some open set, must be 0 on some open subset of R. Okay, so how to solve it? So observe one thing, that how to solve it? Observe one thing. Okay, so if f is identically 0, then we are done. Why? Because f is identically 0, then you can take any open subset inside 0 comma 1, and that will give us the answer, right? So we may assume that f is not identically 0. That means f of x is not equal to 0 for some x, or sir, I should write x naught, right? So now if f of x naught is non-zero, since f is continuous, there is a neighborhood such that f doesn't vanish, right? So it's a property of continuous function, or you can think it graphically. So suppose you have this, at some point this is non-zero, then you can always find a small enough neighborhood of this such that this function is non-zero always, right? So because of the continuity property. So then choose open subset u, or I should say open interval u, such that f of x is not equal to 0 for all x in u. But now since f dot g is 0, this implies g of x must be 0 for all x in u. So this is the open subset on which g is 0. So that's why we are done, because the question says that either f or g must be 0 on some open set. So if f is not identically 0, we can always find a open set g such that g must be identically 0 on that. Because if you choose some point where f is non-zero, you can always find a small enough neighborhood which is small enough in open interval containing x naught such that f doesn't vanish on this. So that means g has to vanish, right? Because f dot g must be equal to 0 by our hypothesis. So that's why it is done. That's why g must be 0 on some open set. Okay, so that's why question number 20 is also fine. So now only one question left, that is, let L1 be a line in R2 joining 0 0 and 1 by 2 comma 3 by 2, and L2 be the line in R2 joining 0 0 and 3 by 2 comma 1 by 2, right? So let's draw the line. So this is basically, I can write this is the origin, 1/2 comma 3/2, right? So then this is actually 30 degree, because it is sine 30 comma cos 30, right? 1/2 comma root 3/2. And similarly this is actually 60 degree, because this is root 3/2 comma 1/2. Okay, so this line is actually L1 and this line actually L2. Now we are considering reflection. So observe that reflection, if you have a reflection, then it is actually self inverse of its, right? You want to construct a group generated by these two inside the subgroup generated by these two inside the automorphism groups of R2, and you want to find its order. That's the main thing, right? So now if L1 and N2, if they are the elements, if you denote it that, so G is actually subgroup generated by L1 and L2. So first of all, L1 square is identity and L2 square is identity, because L1 and L2 both are reflection, right? So then we need to, the extra thing that you need to find, that is L1 L2. This is, so L1 L2, what is that? So basically reflection, right? So what is that? What is this composition? That's my question. What is this composition? Okay. So what is it? So if you see how to see it, so if you start with any point, say any line like this, if you reflect it with respect to this L1, what will you get? Right? So it is better that I should write, say start with this, say this is the angle theta. Okay, so then what will be this? If you reflect first here, this will be 30 plus theta, right? 30 plus theta. Then what will be this? After reflecting with this will be what is this angle? This will be 60 plus theta, right? So it's actually composition of these two, it's actually rotation by 60 degree. Can you observe it properly? Just takes very simple example. So let's take this one, this x-axis. So this is 30 degree, right? So if you reflect it, this will be on this axis, 60 degree axis, right? This thing. But with respect to this, if you reflect it, this will be same as this. So total it is rotated by 60 degree, because this is 0 degree. If you take this x-axis, this is 0 degree. Similarly, if you have a positive thing, then it is actually rotation. This composition L1 L2 is actually rotation by 60 degree. So then what is L1 L2 power 6? This is identity, right? So L1 L2 power 6 is identity. Now try to show this is actually D6, because you have a rotation, you have reflection, and rotation power 6 is identity. So it's actually, you have a 60 degree rotation. You try to show that this is actually D6. It's not very difficult, because you have element L1 square L2 square is there, right? And L1 L2 you know. What about L2 L1? L2 L1 should be rotation by 300 degree. Okay, that's the thing, rotation by 300 degree or something like that. Okay, it depends on the case, but I'm not sure, but one can check this. Okay, but the idea is this, that this is D6, because you have the 60 degree. So when you get that 60 degree rotation, then it is automatically true that these are 12 elements, because D6 has 12 elements. So it can be done. So you have to just show that there is some natural isomorphism from that to that, or you can just check element wise, because these had two rotations, so L has some power, maximum power 2. So your element should be L2 L1, L1 L2, L1 L2, L1 L2, something like that, right? And L1 L2, L1 L2 square, that is must be the rotation by 120 degree, and you can have L1, L2, L1, that kind of element. So just observe this, okay? So then it will be done. Okay, I don't want to make this video long, so that's why I'm not proving it explicitly, but this is the idea, that in this way you can solve this problem. So this is the way that you can solve the TIFR previous year question papers, and in next video I'll try to explain the other 20 problem, the MCQ problem. But this is the entire video, and this is the thing. Okay, I hope this is clear. Okay, if you are not able to understand anything at any moment, then please comment below, I will explain you. Okay, no problem. Or if you have some different kind of solution which you feel that much more easier, or even if it is not easier, if you have some other solution, then definitely comment below, because different solutions will help us to understand better. Okay, and if I get some new solution, that will be helpful for me also. Okay, so definitely try to comment. Okay, so if you have different solution. Okay, thank you. Okay, and soon I will upload the other part also.